Positive whole numbers a and b satisfy this equation. We're asked to find all possible values of a. Now, this is actually a Diophantine equation, but it's already been factorized, which is great, because all we need to think about is integers that multiply together to give 45. However, they're non-zero, so we only need to think about the positive integers. So let's look at the factors of 45. You could write 45 as a product of prime factors. It's going to be 3 squared times 5. In fact, that gives you the number of factors. You take the powers, you add 1 to them, and you times them together. So 3 times 2, 45 is going to have 6 factors. Okay, it's not so bad in this case to write them down. We'd see quite quickly, yeah, 3 is going to go into it, and 15, and then 5 and 9. So there we are. Okay, so now I'm going to look at a plus b and a minus b equaling these numbers. Remember, they're positive, so we can't have negatives, but that is something that you could potentially get as solutions, but not in our case. Then we can work out a and b from this. Now, because they're positive, this one's definitely going to be bigger than this one. So I don't actually have 6 possibilities. If I want to use 1 and 45, this one is going to have to be 45 and this one 1. And then if I want to use 3 and 15, the left-hand one's 15, this one is 3. Otherwise, you'd end up getting a is negative. So I think that's the case anyway. Yeah, if a plus b was 3, no, b would be negative. And then this one would be 9 and 5. Okay, so I've sort of created some equations here. Well, not sort of, I have. So a plus b could equal 45, and then a minus b could equal 1. If I want to solve that, I can add them together to give me 2a equals 46, and therefore a is 23, and b would then be 22. I can do the same for the others. I can add them together, divide by 2. That'll give me the value of a. So in this one, a is 9, and b would be 6. And this one, I get 14 when I add them, divide by 2. We're going to get 7 and 2. And that is it. Those are the only possible solutions where they're both positive. Just to say, like, if I used 5 and 9, then I would get what would I get? A equal to 7 again, but then b would have to equal minus 2. So that's why I don't need to look at any of those. A plus b is the larger one. So yeah, find all possible values of a. Here we are. Let's just list them. 7, 9, 23. Let's take a look at the next part. Priya and Ria each create a sequence of positive integers. Priya starts with 1,000 and adds consecutive odd integers. So 1,000, so adds 1, adds 3, and adds 5. And what we seem to be getting is the units digit is always a square number. The next one we'd add 7, we'd get 1016. And actually that will always be the case because look, when we've got 1, that's a square number. And then if we add 3 on, you can make a little 2 by 2 square using that. And then if we add 5, go along and make a 3 by 3 square, add 7 and so on. So always just adding on an extra 2 each time. Continue in this square idea. So the nth term is going to be 1,000 plus n minus 1 squared, because when n is 1, I'm still getting 1,000. So I'm going to go with the typical kind of sequences form here. I have seen solutions where they just wrote n squared for some n, and n could then be 0, but I think I'm going to stick with this, although we will make a little substitution in a minute. Now for the other one, it's going to be 3,025, also adding consecutive odd numbers. Well, I'll write it down, 3025, then 3026, then 3029, and then 30, so I'm adding 1, then 3, then 5, 3034. And now I'll say Vn, the different nth term, is going to be 3025 plus, actually I'm going to call it I'll call it n, n minus 1 squared. And I want to know how many numbers appear in both sequences. So what that means is I'm going to need to set my terms equal to one another. 1,000 plus n minus 1 squared is going to equal 3025. Now be careful, I actually don't want to use an n here because then I'd be looking for where it's like the same value of n in the same in the sequences, and we're never going to get that. You're not going to have the third term of one equal to the third term of another. So I need to use an m or something like that. This is what I'm going to try and solve. So then I can minus 1,000 and minus the n minus 1 squared. So n minus 1 squared minus n minus 1 squared is going to equal 2025. That number's coming back into it. And what I'm going to do is now let a equal n minus 1 and b equal n minus 1. This just makes it a little bit nicer. So a squared minus b squared is going to equal 2025. We've got ourselves another Diophantine equation because these have to be whole numbers. In theory, they could be, so n, remember, is 1 onward. So a and b could, in theory, be 0. And actually, that will be a solution because 45 squared is 2025. And I think actually that gives us the 3025 overall, because 1,000 plus 2025, that 45th term could be 3025, and then when n is 1 in the red one, we'll get 3025. But anyway, I'll just write a, b greater or equal to 0. So not strictly positive. Okay, to solve this, we can do a similar thing to the previous part. This is a difference of two squares. We can factorize it. A plus b times a minus b is going to equal 2025. And let's deal with this in a similar way to part A. So I've got a plus b, a minus b. And from that, we can work out a and b. From that, we can work out n and m, because n is actually a plus 1 and m is b plus 1. And we don't need to find all these values out, because actually in the question, there's two things we've been asked about. How many numbers appear in both sequences? So how many solutions are there? And then find the second smallest number that appears in both sequences. We already have the first, remember, it's 3025. So for this, I need my factors of 2025 again, but they're going to be the products. So we've got 2025 here, and then this one will be 1. And if I wanted to solve this to find a, I could again add them together and divide by 2. I'm going to get 1,013. And then this will be 1,012. Now to add 1 here to get 1,014 and 1,013. So that'll be a solution. And then just going to write down other factors. I will talk about how you could avoid doing this in a minute, but I think I don't know, this is how I did it. So 6, 7, 5, and 3 will work. And then 405 goes with 5. I'm trying to write them in order here, although that is not actually going to be essential. 225 goes with 9. We've also got 135 that then goes with 15. Remember that a plus b must be bigger than a minus b, because otherwise you get a negative for b, which we can't have. So I only need to consider, yeah, the upper half of the factors. After that, I've got 81 and 25. 75 and 27. 45 and 45. 1, 2, 3, 4, 5, 6, 7, 8. And that is going to be it. There are going to be 8 solutions here. The way we could have done that without actually writing any of them down, ever calculating all of the factors, would be to realize that, okay, there's 15 factors, so there's going to be 7 in the upper half and 7 in the lower half, and then 1, which is the 45 times 45. that 45 gives us, a possibility as well. So I'm going to take these 7, I'm going to take this 1, and then there's going to be 8. You just also have to justify that they're going to always be odd, but they are because the prime factorization only includes odd primes. Because if you had an even and an odd, when you added them together and divided by 2, you wouldn't get a whole number. So that's kind of in there anyway. So I feel like quite a safe approach is just to do what I've done, and then probably still explain that you could work them all out, but you don't want to lose time if you can avoid it. Just explain that they're all going to give you odd answers here and be valid. This just leaves us with the very final part, which says find the second smallest number that appears in both sequences. Now, I mentioned this earlier, but the smallest would be that 3025, and it would come from the 4545 solution because it gives A equal to 45, B equal to 0, and then N is going to be 40. Oh, sorry. Yeah, N is going to be 46, and then M is going to be 1. Remember I got a bit confused there, but when I put it back into my nth term, remember I still need to minus 1 from them. So I will be doing 3025 plus 0 squared in that case, and 1000 plus 45 squared in that case. So really, I'm not really that bothered about N and M. It is all about the A and the B because I might whatever I get for N and M, I then minus 1 from it. So the second smallest is going to be my second smallest value of A and B, and that is going to be this one here. So if I add these two together, I'm going to get 90 plus 12, which is 102. Divide by 2 gives me 51. And then for this one, I'll get B, I'll get 24. And that'll give me, yeah, my second. So if I take the 1000, for example, yeah, it'll be 1000 plus 51 squared. You can find the n, which is 52, and then minus 1 from it, but that will be equivalent. And all the rest is going to be bigger, because I'll get a larger value of A when I add these together. So find the second smallest number that appears in both sequences. It's going to be 1000 plus 51 squared, which is going to be 1000. Now 51 squared is 50 plus 1 times 50 plus 1. So I have 2500, and then I get 100, and then I add 1. So it's going to be 3601. Okay, nice question. Just to summarize, we dealt with the Diophantine equation. It had already been factorized. This guided us along the part A. We found 3 solutions. B was obviously a step up. I wrote down the nth term involving square numbers, set them equal, but just used an m now. Replaced n minus 1 and n minus 1 by A and B respectively. Could have gone with that from the start. It just felt quite natural to use the nth term personally. But we didn't actually then need it from that point on because once you've got A and B, you can just sub them straight in to get the terms in the sequence. But solve this one, difference of 2 squares to factorize, wrote down all the possibilities. There were 8. Could have done it quicker by just realizing there's going to be 7 below the square, the 45 times 45, 7 above. We're going to get 7 from that and 1 from the 45. Just justify that they're all going to be valid because they're all odd numbers. So you're going to get an integer value for A. The smallest one was the 45, and that gave us the 3025. The second smallest is the second smallest value of A, which we figured out was 51. Put that back in to get us our answer of 3601, and we're there.